Hello everybody and welcome back to another video. In this video, we will be doing some F is equal to MA practice. Now this exam is coming up in less than a month now. I believe it is on February 12th. And this problem, although it likely is far too long to be on the exam itself, I believe that this is good practice for the exam. So to begin, let's look at the question itself. So an object with a moment of inertia given by the formula I is equal to kmr squared, such as right here, is placed on an incline with an angle theta above the horizontal and a coefficient of static friction given by mu s. So this surface right here has a coefficient of static friction given by mu s when it is between this object. Now find the maximum value of theta such that the object rolls without slipping. So to begin, let's first look at the free body diagram of this object. So let's draw this out right here. So this is at center, there's a force of friction this way, and which is force of static friction in this case, since we are looking at for the maximum angle where that is still static friction. Then there is a normal force right here, starting from the point right here on the incline. Then at the center, there is a force of gravity directly downwards, which can be broken into components in the direction of the falling and away from the movement. So what we could say is that since there is no acceleration in this direction, Fn must be equal to this component right here, which we will call Fg perpendicular, since it is perpendicular to the surface. And through basic trigonometry, you should just have this memorized. Fg perpendicular must be equal to Fg cosine theta, which is equal to mg cosine theta. So that is equal to our Fn. And we also know that our force of friction, when it is static, must abide by the following formula, where it is less than or equal to Fn times the coefficient of static friction. However, since we are finding the maximum value theta before it slips, that means that this force must be at a maximum before it's too strong and it just converts to kinetic, and this coefficient would actually go down. So that means that our force of friction is equal to our coefficient of friction times Fn, which, if we remember, that is just given by mg cosine theta. So this is the formula we get from that. So this is our force of friction, and the only force that causes a torque is actually going to be that force of static friction, because Fn is perpendicular, or is parallel, I guess you could say, and it goes through the midpoint if you use the parallel axis theorem to change it to right here. Then we have a force of gravity going right here, which is just at the point, so it does not contribute any torque to the system. So we only have one force that contributes torque, and we could say that torque is equal to the net torque is equal to the sum of all the torques, which is equal to I times alpha, which, if we remember, I is just kmr squared. So this is kmr squared times our alpha, which is just our acceleration divided by our radius, which is equal to mu s mg cosine theta multiplied by r, which is the radius of our sphere. So this is mu s mg cosine theta, and we can go ahead and cancel out these m's, and this r cancel, and then there's an r over here that I forgot to add before, and this r cancel, giving us a statement that k times a is equal to mu s times g cosine theta. Now, I put that a in parentheses for reasons that you will see later. It will just make it easier for me to explain this to you. But now let's look at the net forces on our system. So if we go by forces, then we know that F net is equal to the sum of forces, which is equal to ma. And the sum of forces, since this force and this force contribute no acceleration to the system, and they cancel each other out, we know that this force minus the force of friction is going to give us our net force. So this is Fg parallel, we can call it, And through some more basic trigonometry, we get FG parallel is equal to FG sine theta, which is equal to mg sine theta. Now we can plug that in, and this is mg sine theta minus our force of friction, which is mu s mg cosine theta, and that's equal to ma. Cancel out all the m's right here, and we get the statement that A is equal to g sine theta minus mu g cosine theta. Now, if you remember, we have this A right here multiplied by K is equal to this right here, and we have two unknown statements right here. We do not know our A and we do not know our theta. Everything else is a constant that is given. So what we are going to do is plug this A in right there. And this is just a normal A, not an alpha, even though I drew it kind of weird. So when we plug this in for our A, we get K times this statement right here, which is kg sine theta minus k mu g, this is mu s, cosine theta is equal to our mu g cosine theta. Now, since we have g everywhere here, we can just go ahead and divide it out, and this gives us that k sine theta minus mu, this is k mu, so mu k, mu sk, cosine theta is equal to mu s cosine theta. And you might be thinking, well, how do we solve this? This looks incredibly strange, and you can't solve something that has sines and cosines without an approximation. Yes, you can. Divide everything by cosine theta in this equation, and this cancels these guys out and creates this into cosine theta divided by, or sine theta divided by cosine theta. That is just tan theta. So we get the equation k tan theta minus mu sk is equal to mu s and no cosine theta because I canceled out over there. And now we can just add mu sk and divide by k, and this gives us that tan theta is equal to mu s over k plus mu s. Since we divided by the k, that k went away and that's divided by it. And this gives us that our angle theta is equal to the tan inverse of mu s over k plus mu s. So this right here is our answer. So I hope you all enjoyed this video. I hope that you learned a lot, and good luck to those of you who are taking this exam. And for those of you who aren't, I hope you enjoyed the video and enjoyed the process of solving this very intricate problem. So thank you for watching.